With the session. First of all the speakers, if you haven't done it, you should send the presentation to the email that's written here. What's your name? Ijo Shu is going to talk about fundamental limits of matrix sensing, exact asymptotics, universality, and applications.
Hello, thank you for coming. Now I will talk about our paper about the fundamental limits of matrix sensing, and our main result will be about its exact asymptotics and applications. This is my joint work with Anton, Lenka, and Florent. So first, let me introduce the matrix sensing model. So the matrix sensing model is basically a generalized linear model, but the signal here is not IID, but a high-rank matrix, S star. So the goal is to recover the high-rank matrix S star from noisy observation Y. And here phi is the sensing matrix, but it might not be Gaussian, and it can be more general. And here Z represents the Gaussian noise, and phi is an arbitrary nonlinear function. So this is basically a generalized linear model with matrix signal. And we will consider the high-dimensional limit that the rank of the matrix S star is proportional to its size, and they go to infinity together. So this is a very challenging regime because most previous papers focus on the case that the rank of S star is finite, and here it goes to infinity. And in the high-dimensional limit, the number of samples n is proportional to the number of unknown elements of S star. And the goal of this paper is to characterize the optimal learning by computing the minimal mean square error, which is the mean square error that is achieved by any estimator. And it is also the mean square error achieved by Bayes' optimal estimator. Okay, so there are two motivations for us to analyze such a matrix sensing model. The first example is a teacher-student model of a two-layer network with quadratic activation. On the right side, it is a two-layer network, and double star here is the weight of the first layer. And from the formula on the left side, we can see that if the activation is quadratic, then the two-layer network is just a matrix sensing model. It's a matrix product between phi and S star, and here the sensing matrix phi is XX transpose, which is a rank 1 sensing matrix, and S star is a sum of W star transpose. And we will consider the case that the input data X is sampled IID from Gaussian distribution. And we will consider the challenging extensive width limit, that is, the input dimension D goes to infinity, and the number of neurons M is proportional to the input dimension D, which also goes to infinity. And also the number of samples N is proportional to the number of elements in the weights W star. So in this limit, we can see that S star is just a high rank V-shot matrix. Okay, so this is covered by our general model. And the second motivation is the bilinear sequence regression model. So we can represent a sequence as a matrix X. For example, a sentence. The length of the sequence is L, and each element of the sequence, for example, each word is embedded in dimension D. So basically, a word is a D-dimensional vector, and thus the sequence is a matrix X of dimensional D times L. And the observation here is a bilinear model on X, and the weights are U star and V star. Okay, so we assume that the prior of the weights U star and V star are Gaussian, and our goal is to recover the weights U star and V star from the observation Y. So this is again a matrix sensing model. And we will consider the limit that the sequence length L is proportional to the input dimension, which goes to infinity. Okay, so this is also covered by our general model. Okay, so then I will talk about the main results. First, it is an assumption on the signal S star. And for simplicity, we will describe our result in terms of symmetric S star, but the same holds for asymmetric S star. So for symmetric S star, we assume that we assume that S star is rotationally invariant, which means that its prior takes this form. And the function V is called the potential. And here we assume that the potential is continuous and strongly convex and is supported on an interval. And this covers many important examples, including Gaussian matrices and Wishart matrices. And we have a similar assumption that is for high but no non-full rank matrix. For example, non-full rank Wishart matrices. Okay, so next is the assumption on the sensing matrix phi. So assume that the sensing matrix satisfies a uniform y-dimensional central limit theorem. So basically, this means that the trace of phi s is converges to the trace of gs, where G is a Gaussian matrix. So this basically suggests that the sensing matrix phi is similar to a Gaussian matrix. And we assume that this property should hold uniformly for any S that has bounded eigenvalues. And important examples of the sensing matrix phi including matrices with IID entries, including, of course, Gaussian matrices. And also centered rank 1 matrix, XX transpose minus identity. So the second case is important because we have just seen that for two-layer network, the system matrix is just a rank 1 matrix. Okay, so under these two important assumptions, we can state our main results regarding the limit of the mutual information, between the signal S star and observation Y. So this mutual information can be written in terms of the saddle points of the replica symmetric potential, IRS. And the replica symmetric potential, I, is conjectured in previous paper, but is rigorously proved in this paper. Okay, so it takes an explicit and easy to evaluate form. And there's an important remark that here psi out is determined by the nonlinearity and is similar to previous literatures. But the psi p0 here is the mutual information of a matrix denoising problem. The matrix denoising problem is the problem that we have a noise observation of the rotational invariant matrix S star, and we want to recover S star from its noise observation Y. Here, Z prime is Gaussian noise. So this kind of matrix denoising problem is well analyzed in random matrix theory, and we know its mutual information. Okay, so after obtaining the mutual information, we can have the MMSE, which is written in terms of the maximizer of the replica symmetry potential. And the idea is that MMSE is directly related to the mutual information by the so-called IMSE theorem. So after introducing a side channel, we only need to take a derivative of the mutual information, and then we can obtain the MMSE. Okay, so this is the MMSE for the matrix sensing problem, and we can go back to our application that is introduced at the beginning. So for the two-layer neural network, we can define the test set that is sampled ID from Gaussian distribution, and the test label is given by the teacher network. So the generalization is the generalization MMSE is the mean square error, the minimal mean square error that is achieved by any estimator Y hat. And it is also the mean square error corresponding to Bayes optimal estimator. Okay, so we can have the limit of the generalization MFC that is given similarly as the previous theorem, and we only need to take the activation to be linear and the V-sharp matrix, the V-sharp prior, and we need to take the prior to be the V-sharp prior. This is understandable because we have shown that the two-layer network with quadratic activation is equivalent to a matrix sensing model with V-sharp prior. So their MSE are directly related. Okay, so finally this is the sketch of the proof. So there are 3 steps. The first step is Okay, is that under the one-dimensional central limit theorem assumption, we can show that we can replace the data matrix with a Gaussian matrix. And then after having the Gaussian matrix, it becomes a generalized linear model. And we can use the adaptive interpolation method. But the adaptive interpolation method is for ID priors, and we generalize it to structured matrix priors. And finally, after using the adaptive interpolation method, it reduces to computing the MMC of a denoising problem, the matrix denoising problem. And this can be computed by random matrix theory. There are some future directions. This paper is about Bayes' optimal performance, and it is still need to study the computational hardness of this problem. Okay, and the second is to characterize other estimators, for example, empirical risk minimization or gradient descent. And finally, I have mentioned that two-layer network with quadratic activation is equivalent to matrix sensing model. And for polynomial activation, it becomes the tensor sensing problem. And here the signal becomes a tensor. And such a tensor problem is still an open question. Thank you for listening.
Any question? Yeah.
So the classical adaptive interpolation
Yes.
requires something like the overlap concentration.
Yes.
To obtain
Yes, we have to prove the same thing. It over-
by random matrix theory.
Yes,
Okay, cool.
by its concentration.
Thanks.
Another question? Okay, let's thank the speaker.
Thank you.
Okay, Ramesh Paul is going to talk about robust algorithms for recovering planted colorable graphs.
So I'll be Can you start that again? Yeah. Okay. So I'll be talking about robust algorithms for recovering planted colorable graphs. This is joint work with my advisor Anand Luis from Indian Institute of Science, Bangalore, and Prasad Raghavendra from UC Berkeley. So start with the widely popular planted clique problem, where we plant a clique or equivalently an independent set of size k in a random Ado-Chenier graph. And the goal here is to recover this planted independent set, or a seemingly easier goal is to even distinguish this from a random Ado-Chenier graph. And if the planted set has size larger than 2 log n, there is enough information here to do this, but we only know of computationally efficient algorithms when k is at least square root n, and this is the famous statistical computational gap for this problem. Algorithmically, we can look at the degrees and distinguish based upon the degrees with the threshold square root n log n. We can also get square root n by looking at, for example, this spectral test, which looks at the signed adjacency matrix. So for p equals to half, this is just the plus minus 1 matrix. And if you look at the magnitude of the largest eigenvalue, it is for a random graph square root n. For the planted graph, it is k, and if k is much larger than square root n, you can distinguish. This can also be turned into a spectral recovery algorithm by looking at the appropriate eigenvector. And this is the best we know for this problem up to some constants. In fact, there are lower bounds known for class of algorithms like sum of squares algorithm, which show that it may be hard to improve upon this. Then people start looking at these more richer models, semi-random models, where you allow an adversary to interact with the graph. So this can't be an arbitrary adversary because these are NP-hard problems, so it will just hand you the worst case instance of the problem. Also, it has to respect the planted structure. So the first step in this direction is to consider a monotone adversary, which in this problem can only add edges in the graph other than the planted graph. These are really helpful adversaries because if you look at the set S, it looks even more hollow now from a distance. So these are really helpful adversaries, but combinatorial and spectral algorithms I talked about in previous slides are not known to work. And we can recover at the threshold of square root n, but you need the power of SDPs to do this. But the model that really upped the ante in this line of work is this model from Feige Killian. And this is a very powerful model which says that the subgraph on V minus S could be an arbitrary graph. And even the randomness in the cut S and V minus S is subject to a monotone adversary like the one I talked about. And in a very interesting line of work, we can recover. What recovery means is slightly different, like the appropriate notion of recovery. We can do that in a slight variant of this model up to the threshold square root n log n, which by the way is also the information threshold, the conjectured information threshold in this model. Yeah. So why should we care about semi-random models? I'll refer to you this excellent book by Tim Ruff-Garden. Broadly, it says that it allows us to navigate what are the right models for the problem and what are like the robust algorithms. It also allows us to understand structurally what makes a problem hard. And this is not just exercise in philosophy, it also has consequences. Like you can port these insights to make progress. For example, this for densest K subgraph problem, we can do this. So in this spirit, we ask this question: what other planted structures can you recover? So in this work, we consider this model. Firstly, let's look at the random planted model for R-colorable graphs, subgraphs, where we plant an R-colorable subgraph. So these are R-independent sets, R-color classes. But importantly, note that they have arbitrary edge structure in the color classes. The edges between the color classes are arbitrary, and the rest of the graph is random. And also we consider a corresponding semi-random model where, and this is an interesting semi-random model, it's sort of orthogonal to this very powerful Feige-Killian model I talked about. Here the edges in S cross V minus S are arbitrary, and the V minus S is a random graph, but that randomness is subject to a monotone adversary. Yeah. So let's look at some simple ideas. Firstly, you could try to say this is, okay, so for the rest of the talk, I'm going to focus on the case of R equals to 2 because most of the ideas are there. And I'm even going to focus on the random model. So firstly, you could say, okay, these are two independent sets. S1 is one independent set. I can just try to first recover it and recursively run the maximum independent set algorithm. But the issue with that is something like this. But the issue with that is that the edges at the boundary of the independent set are arbitrary edges now. And there are no guarantees known, in fact, in this model. Even the state of the art, they assume some randomness between the cut edges. At the other end, you could say, there are very general densest K subgraph algorithms. You could try to run those algorithms, but then, you could have the degree, the average degree of the planted subgraph, same as the ambient degree, and the vertices are really indistinguishable. You can do a small calculation to check this. But then the question that you should be asking is that we have a planted structure. We don't have an arbitrary dense graph. We have a planted structure. Even when D is roughly pk, we should use that structure to our rescue and recover in this model. Also, I talked about this eigenvalue based test. So does that work? Well, for R equals to 1, it did. Even for general R, you can have this test can work. But turning that, so that test can work to distinguish the problem from a random graph. But turning that into a recovery algorithm is a nightmare. I'll spare you the details, but I'm happy to talk about it offline. So a closely related work appeared at this venue in Col 23, where they consider this planted R coloring problem, but the edges between the color classes are random instead of arbitrary. And they show that you can actually generalize the degree counting algorithm to recover in this regime, but not that we have arbitrary edges between the color classes, not random edges. But importantly, they also, the main result in that paper is to give a lower bound, which says that you cannot recover in small of R square root n, assuming the planted Lie hypothesis. And that also applies in our model. There are some other work which consider special cases, but we can in fact give a general result, which we can give a result in the general setting, which recovers at this right threshold, which is R square root n up to some constants and some dependence on P, which may not be optimal. We can almost recover a graph. We can give a 1 minus delta times the planted set with high probability. And note that this matches the lower bounds from this paper. So about techniques, we use SDPs to do this. The idea that I said that you can try to recursively try to find an independent set. We ran into some issues trying to do that, but SDPs can do that. They can do search for, what they can do is they can search, instead of doing it recursively, you can do search for all independent sets all at once simultaneously. And I suggest you not to look at this SDP, but look at this diagram instead, where what we are saying is for every, so there is a vector for every vertex and every color class there. For example, there are 2 color classes here. the SGP tries to say, what the SGP tries to do, the intended solution is that you try to have a vector, a unit vector for every color class, and you try to keep the color classes far away from each other. And then SGP really rewards if the color classes, the vertices in the color classes like align with the corresponding color class. It's a kind of cluster together. So the SGP rewards that. And yeah, so this has this pronounced geometric structure in this SGP, which is what people call crude SGP because of this constraint. And yeah, so this is the SGP. I'll let it stay for us. Second, and the analysis is that, the analysis is pretty clean. You can just look at this SGP solution and the mass on V minus S, this thing that I've circled here. If you can show that this is at most square root, if you can show that this mass is small, you are done, because you can just run a simple rounding algorithm that looks for large vectors and rounds that to, and gets a planted set from that. To show this, this is the main lemma in the paper, that you can show that if you look at the optimal solution and the mass that it has on V minus S, the subgraph induced on V minus S, we can bound that using the theta function on the graph induced on V minus S. And this is the Lova's theta function I'm talking about. And if you can do this, then we can use a well-known result about bounds on theta function. And we can plug those here and we can get the circled inequality. And the way to do this is, what we can do is you can look at the optimal solution to your SDP. And from that, you can construct a solution to the Lova's theta SDP. And then you can do a simple calculation to show, I skip the details, you can do a simple calculation to show that indeed this lemma holds. I'll talk about a few future directions for this. So firstly, in this model, how do you even recover all the edges of the planted subgraph? Even the clique, let us say. It's not clear if you can recover 1 minus delta times 0.99 fraction of the whole vertices, but even the planted clique problem in this model, where you have arbitrary edges in S cross V minus S, how do you even recover in the R equals to 1, it is also not clear, and more generally, how do you recover edges? Also, the dependence on P, we do allow P equals to small of 1, but we did not optimize for the dependence upon P and delta, and there may be again sharp threshold phenomena here, which may be of interest. Then again, I talked about spectral algorithms. There are a lot of issues with that, but it would be very nice to have spectral algorithms which can do the same task. And more generally, you could ask this question, what other planted structures can you plant and recover in such models?
Any question? So I can ask you a question. So the Lova's theta function, it's somewhat understood for many graph structures, right? So, so maybe are there directions that you study, like specific types of graphs, or like something?
Yeah. So if if a graph has, so we only use the bound square root n on the Lova's theta function for a random graph. So there are other graph classes where, if that bound holds, you can also get a recovery algorithm there. But the more interesting problem is that, okay, even for the clique, like the bound is tight, so you will not get extra mass for for random graph. We know that it is the theta function is theta square root n. So how do you even fully recover the clique, because you will not get extra mass from you will have some mass on V minus S because of the theta function. So yeah, there are other graph classes where the theta function value is bounded and you could recover those as well. Yeah.
Okay, thank the speaker again. Or is there any question? Or? Okay, thank the speaker. And
subgraphs in random graphs. This is a joint work with Wasim Khulechel. I want to start with two simple examples. The first is a one that you probably all know of, the planted clique model. And in the detection problem in the planted clique model, we want to distinguish between two hypotheses. In the first, we just view a plain Erdos-Shani random graph with an edge probability of, say, half. In the second hypothesis, we have an Erdos-Shani random graph, but now with a clique of size k planted inside of it uniformly at random. And the typical question is how large should the clique be such that we can distinguish between these two hypotheses. For a clique, this is all well known. So it is well known that the statistical barrier is at 2 log n. And it is also conjectured that there is a computational barrier at square root of n, meaning that we conjecture that there is a statistical to computational gap. The second example is the one of a planted path studied by Musali, Stefan, and Tausley, where we plant a path of size k, of length k, inside a sparse Erdos-Renyi random graph with an edge probability of lambda over n, where this lambda is a constant, and we ask the same question. And what they discovered is that there are two main regimes. The first is where lambda is smaller than 1, and the second is where lambda is larger than 1, where we have different statistical barriers. And what's interesting is that they also discovered that there is no hard phase. Whenever detection is possible, it is also easy, meaning that in contrast to the planted clique problem, there is no statistical to computational gap. And beside these two examples, there are many other examples in the literature for different kinds of planted structures studied in this context. And in this work, we are going to give a general theory for arbitrary planted subgraphs. One can ask, why do we need a general theory? So first, as we noted, different planted subgraphs can have very different statistical behavior. So we are interested in the question of what graph theoretic properties determine these statistical behaviors. And another important aspect concerns with the mathematical techniques. So in the literature, different planted structures required tailored analysis and tailored techniques. And we are interested in finding or establishing a technique that captures all planted subgraphs together. And finally, we are concerned with the computational aspect. So as we saw, some planted structures have a computational to statistical gap, and some structures don't. And we are interested in finding out which or what makes a planted subgraph hard or easy to detect. There were some attempts in the literature to give some general theory. Most related to this talk is a paper by Berry et al. that studied general lower and upper bounds in the detection problem of general combinatorial structures in random matrices. But if you try to apply their bounds to the planted subgraph problem, you get loose bounds in general. A second closely related paper is the one by Yu et al. That studied the detection problem for arbitrary planted subgraphs, but only using a specific class of algorithms that uses constant degree polynomials. Okay, so now let's define the problem formally. We have a gamma, a sequence of planted subgraphs. It's a general sequence. And we think of our problem as a simple hypothesis testing problem, where under the null measure, we view just an Erdos-Renyi random graph with an edge probability of Qn. And under the alternative hypothesis, we have a planted distribution generated by first drawing a copy uniformly at random from the complete graph of n vertices, then including the edges of this copy to G with probability Pn, and the remaining edges are included to G with the probability of Qn. And our goal would be to find out the conditions on this sequence such that the optimal error probability is small. Let's move on to the main results. So let me just mention that we have bounds and results for any sequence and for any values of Pn and Qn. But for simplicity, let's focus on the dense regime, where we, loosely speaking, assume that Pn and Qn are constant. One important quantity for us is the maximal or the maximum subgraph density, defined to be the maximal value of the ratio between edges in vertices over all subgraphs of gamma. The main theorem that we have says that the statistical barrier is given by the maximum of these expressions, these ratios, the ratio between the maximum subgraph density and log n, the number of edges in n, and the square of the maximal degree relatively to n. And if this maximum is large, then strong detection is possible. If it is small, it is impossible. We also note that if gamma has a sublogarithmic maximum density relatively to the number of vertices, then this term vanishes, and it turns out that whenever detection is possible, it is also easy, and there is no statistical to computational gap. This is, for example, the reason why we don't have a statistical to computational gap in the case of a path that we saw, or a star, or a tree, where the maximum subgraph density is bounded by 1. Okay, what about subgraphs with superlogarithmic density? We have a theorem saying that the computational barrier is given by the maximum of these two fractions. And again, whenever it is possible, we have two efficient time algorithms that work. And when it's small, under the low degree polynomial conjecture, we have that no polynomial time algorithm can detect. These two theorems together closes the deal and completely characterizes the statistical and computational barriers in this detection problem. All right, so now let's talk a little bit about our bounds, starting with the upper bounds or possibility results, which we achieve using a combination of three simple algorithms. The first is the count test that thresholds the number of edges in the graph G. The second is the maximum degree test that thresholds the maximal degree of a vertex in G. Those two tests are works in polynomial time, and they are pretty much well known in the literature. The final test is a variation of what's known to be the scan test, where we have gamma max, a subgraph of gamma that achieves the maximum subgraph density, and the test thresholds the maximum number of edges in a copy of this gamma max inside G. This test is inefficient because the search space could be exponential in size. Let's move on to the statistical lower bound, which is the main challenge and the main novelty of this work. If we want to rule out the possibility of detection, we need a lower bound on the optimal risk. And a typical way to do it is by bounding it using the second moment of the likelihood ratio with respect to the null measure. So we need an upper bound on this second moment, which is widely known.
Are we waiting to fix it, or?
Front right.
Some hypergeometric distribution in the case of and this moment generating function could be hard to bound in general because the distribution of this random variable can be very different from one planted subgraph to another. For example, in the case of a click, this random variable, the distribution of this random variable is related to some hypergeometric distribution. In the case of a path, This is implicit, but we can dominate the distribution of this random variable using some Markov chain. So we needed to take a different approach, and the approach that we took is a Fourier analytic approach, where we think of the second moment as the L2 norm of the likelihood as an element in the L2 Hilbert space. So we can decompose this likelihood using an orthonormal basis of polynomials using Parseval identity. We get that this norm square is given by this sum. Involving this probability, the probability that a uniform random copy gamma contains a fixed subgraph H. So in order to upper bound this second moment, we need an upper bound on this probability. And we can give a bound using, of course, the parameters of H and gamma. And this bound depends on gamma via many parameters. Among them is tau gamma, what's called the vertex cover number of the graph gamma. So when we perform the analysis, we get lower bounds that naturally depends on this vertex cover number that doesn't match to the upper bounds that we have, which are independent of this tau gamma. However, we note that these bounds that we get are tied for a specific family of nice graphs that are balanced in some sense. And therefore, the final step would be to reduce from the unbalanced case to the balanced case by showing a sequence of argument involving the fact that we can always decompose any graph to a union of nice balanced or locally balanced subgraphs. So I think I'll stop here. Thank you. And if you have any question, I'd be happy to answer.
Yeah, are we taking questions now, or how does this work? Anyone has a question?
Hello.
Yeah.
Can you have a brief word? Can you have a brief word on how you decompose the graph into balanced graphs, like some quick remark?
Okay, so it's quite simple. So the decomposition argument works on just taking all vertices which has their degree in some range, and all edges that connects that with these vertices, and each time ignoring the edges from the first parts of the decomposition. So we do it by some kind of induction, but this is basically it. And it turns out to work from some very simple combinatorial arguments.
So like you start with somehow the densest part of the graph, and you remove
Yes,
this part
exactly.
and you iterate.
Yes, so you start with all vertices whose degrees are like the maximal degree.
At least some threshold, right?
Yes.
Yeah.
And then you remove these edges, and then you repeat the same process, but with the vertices with some smaller threshold.
Okay, thanks.
No problem.
Okay, let's move to the last speaker. So Amit Rajaraman is going to talk about the fundamental limits of recovering planted subgraphs.
Hi everyone, thanks for coming. Hi everyone, thanks for coming. Today I'll be talking about the fundamental limits of recovering planted subgraphs. This is based on joint work with my incredible collaborators, Daniel Lee and Fran Pernice at MIT, and Ilya Zardik at Yale. So here's the setup. It's the exact same as in the previous presentation, but I'll recap it anyway. You have some graph H on n vertices, which is fixed ahead of time. Now I pick a random copy H star of this H among all the copies in Kn, and I plant it. This is the red subgraph over here. Following this, I take some graph G0 drawn from the Erdős-Rényi ensemble, and then I take the union of H star and G0. Now I erase these red labels, and my goal is to recover the planted copy H star from the noised up copy H star union G0. So I guess arguably the most famous example of this is when H is a k-clique and P is half. This is planted clique, and okay, it exhibits some very interesting phenomena. And it turns out that this is actually a useful generalization of planted clique. It leads to circuit lower bounds, lower degree lower bounds, among many other things. So, okay, how do we measure recovery? I'm going to be interested in the MMSE in an information theoretic sense, and I'll be measuring the MMSE in terms of the fraction of edges I'm recovering. So, okay, I guess the MMSE is just defined by the L2 error attained by the best estimator, which can be expressed in terms of some posterior distribution on the copies of H and G. And what you should really be thinking of this as is the relative size of H hat, the difference of H hat and H star, where H hat is a uniformly random copy of H in this noised up copy G. Right? So it looks like understanding the MMSE really boils down to understanding the overlap between the planted copy H star and a typical copy H hat in the noised up graph G. Right? So perhaps unsurprisingly, this turns out to be related to these critical thresholds in probabilistic combinatorics, where I want to understand when a graph H begins to appear in G and P as I vary P. And more concretely, in my setup, it'll show up because I'd want to understand when copies of H with a given overlap begin to appear in G. So there's one previous paper on this where they show that for this category of H, which is almost balanced, the MMSE undergoes a phase transition at some critical threshold PC. And as you can see in the picture on the right over here, what this means is that if P is at most PC times 1 minus epsilon, then the MMSE is little o1, so I can actually recover a 1 minus little o1 fraction of H star. And if P is PC times 1 plus epsilon, then the MMSE is 1 minus little o1, so I can only recover a little o1 fraction of H star in G. And the PC they define is inspired by the so-called Kahnkalai thresholds in probabilistic combinatorics, which is yeah, an example of, which is related to these critical thresholds I've mentioned above. And what the motivating question of this paper is going to be is whether we can understand more complicated MMSE curves and H beyond just the almost balanced setting. And I should mention that there's 2 related papers at Colt this year, the previous talk, and there's going to be one more in the random graph session, which you should all go to. So okay, what's our result? We essentially understand the MMSE curves of all weakly dense H, where the number of edges is omega of V log V. So for example, a k-clique where k is omega 1 satisfies this. And what we show is that for graphs like this, the MMSE curves essentially always look like staircases. So instead of a single phase transition from 0 to 1, there's going to be a series of phase transitions. And the MMSE over these multiple phase transitions slowly makes its way from 0 to 1. And furthermore, we understand exactly what new information we're getting at each of these phase transitions. So, at the beginning we can, at the end we can recover a little o1 fraction of the graph, and after crossing the rightmost phase transition, we can recover some fraction of the graph. And we, in some sense, we tell you exactly which part of the graph you're able to recover when you cross these phase transitions. And loosely, this says that the denser parts of H are recovered first, and the sparser parts are recovered later. And the notion of density is in the same sense as in the previous talk, where I actually care about the average degree of subgraphs of H. I'll get into this in slightly more detail in a slide or two. Let me be slightly more formal. Concretely, what we say is that for any graph H, there's going to be a bunch of thresholds, Q1 through Qm, such that if I have P between successive two of these thresholds, then the MMSE is actually going to be exactly whatever this staircase tells you, plus little o1. And furthermore, these thresholds, phi qi, which is the x-intercepts of these phase transitions, can be computed in polynomial time. So essentially, you can like sketch the MMSE curve. Okay, let me explain this thing I said earlier about densest subgraphs being easier to recover. So essentially, the easiest part of H to recover is going to be the densest subgraph of H, which is essentially whatever maximizes the average degree within this graph, right? And even if you look at when H begins to appear in G and P, this density intuitively is what dictates when H begins to appear in G and P. So this is the easiest part to recover and corresponds to the rightmost phase transition. Now, once I cross this phase transition, I can recover J1. And it turns out that the next easiest subgraph to recover, J2, corresponding to the phase transition in the middle, is going to be the densest subgraph of H once I remove this densest J1 part. Right? So I'm going to look at essentially the whatever maximizes the average degree in H minus J1. And so first I recover this thing J1, then I can recover J1 union J2, then J1 union J2 union J3, and so on until I'm able to recover everything, or a 1 minus little 1 fraction of everything. And we call this decomposition the onion decomposition of H, because pink was the color we chose in TIGS. So, okay, why should you believe this staircase picture? It turns out that the way we define these thresholds phi qi, while I won't get into the exact formula for it, they're essentially the points at which many copies of this ith layer, ji, begin to appear in j0 minus ji minus 1. Right? So and because ji was chosen to be the densest subgraph in h minus ji minus 1, the intuition is that if the densest part begins to appear, then there's probably many copies of the rest of the graph as well. So assuming I can recover ji minus 1, if I have many copies of the densest part, then there's also many copies of the rest of H, and I can recover this ji minus 1 part of it, but nothing else. So in pictures, what this says is that, okay, if I'm above this phi q2 threshold, say I'm between phi q2 and phi q1, then, okay, I can recover the j1 part. But even if I can recover this j1 part, there's many copies of J2 and many copies of 8 star, which are in G, and their only overlap with the true planted copy 8 star is going to be this J1 part of the graph. But once I go below phi q2, once I go below the phase transition, the only copy of, every single copy of H in G that overlaps with G1 includes J2 as well. But of course, there may be many copies of J3, which indicates that I haven't crossed that phase transition yet. Let me wrap up real quick. So I guess maybe the most relevant question is whether we can go beyond weakly dense graphs. I guess in this talk, we describe the MMSE curves up to like a little o1 additive accuracy for weakly dense graphs, where E is omega V log V, but okay, can we go beyond this? While I didn't describe some part of our results, we actually have some more general results, which work in the setting of planting monotone properties. And in particular, this does include the setting of sparse graphs. But unlike the results I described in this talk, we're only able to describe the MMSE curves up to constants. So we only nail down these phase transitions up to multiplicative constants. And there's the question of how we can do better. There's this other paper which uses similar statements about the MMSE curve, specifically these phase transitions, to prove a very important ingredient towards the fractional Kancalai conjecture. And one could ask whether our techniques can make progress towards this other second Kancalai conjecture, which is actually unproven. And finally, another question is, what about efficient algorithms? I guess this was partially answered by the previous talk, but I think there's still lots of unanswered questions over here. Yeah, thanks.
Iteratively recover the densest subgraphs, then it should give you some kind of continuous curve. So I don't quite understand what.
That's a good question. I guess I was lying a tiny bit. So I guess what you should really be thinking of is it's not a discrete set of phase transitions, but the result over here only really holds if P is like at least a constant above one of the phase transitions and a constant below the next phase transition. So it's possible, depending on the structure of H, that these things collapse in some way. There is a version of this statement, which we have in our paper, which does still give you some results over there, but it's slightly less clean. Yeah.
Shall I think these QIs, like they are all constants, or they can be vanishing depending on it?
They could be vanishing for general H, but I guess if H was, say, a union of cliques or something, all of macroscopic size, then they'd all be constants. Yeah, I think in the setting where the QI are vanishing, or the gap between successive QI is little o 1, you should be referring to a similar but different version of the statement where we have some results. Yeah.
Other questions?